Then welcome everyone to the Computational Neuroscience #1 session. I will be the first talking, and my name is Raul Grieben, and I'm a PhD student at the Institute of Neurocomputation at the Ruhr University Bochum. And I'm going to present a neurodynamic process model of scene representation guided with the search and scene grammar and natural scenes. Convolutional neural networks are deep neural networks that use one or more convolutional layers. And usually a CNN consists of a feature extraction network and a classifier network on top. Modern CNNs are trained end-to-end using backpropagation. A pre-trained headless CNN can be used as a pure feed-forward feature extractor without the classification network. Dynamic field theory is a mathematical framework that characterizes great activation patterns of neural populations that evolve continuously in time. Neural populations tuned to a metric dimension X, for example, a feature or movement parameter, are modeled as neural activation fields. Stable activation peaks, attractor states of the neural dynamics, are the units of representation in DFT. Depending on the kernel parameters, fields may operate in different dynamic regimes needed for cognitive operations. Sorry. Okay. Some things. Okay. Okay, this is a simulation for one-dimensional neural field. Blue is the activation, and green the input, and red is the output of the field. The video is not playing. Sorry. Okay, well. So at the beginning, we see that the input follows, the activation follows the input until it reaches the detection threshold. Sorry. Okay, I'm not sure why this is happening currently. Okay, sorry. I will make different. So we see that the input follows until it reaches the threshold input and the peak emerges. Importantly, after reaching the threshold, the activation is higher than the input, and this comes from the self-activation. And the self-activation also stabilizes the peak from decay and when the input fluctuates. For example, now the input is below the threshold, and still the peak doesn't decay. Only when the input disappears, the peak will decay. These two instabilities, so the detection and the reverse detection instabilities, are in the origin of sequence generation in DFT. And the next regime is the memory regime. And we will see that after removing the input that induced them, the peaks will stay alive. And memory is essential for goal-oriented cognitive operations. The same is also true for decision-making. And here we see that when there are different computing inputs, this field will select one of them. Okay. So cognitive process and motor behavior are realized through networks of fields. Networks are defined by directional coupling among fields and eventually to sensory motor systems. Autonomous sequence of processing steps emerge from the underlying dynamic instabilities of dynamic neural fields. CNNs are able to extract the complex features needed for object classification, similar to what the ventral stream of human vision does. And DFT delivers the neural processes needed for higher cognition, for example, autonomous process organization, sequence generation, feature binding, and working memory. An interface between them would combine the theoretical strengths of the two frameworks, allowing for complex cognitive operations on natural visual input. We propose that the mapping from the distributed representation of the CNN feature maps to the localist representation of a 3D neural field defined over space and object identity can be learned by using the BCM learning rule. This is also compatible with neural learning process found for the IT cortex. We built upon prior work in which we presented a neural process account for classical visual search experiments and proposed answers to long-standing questions in the field, the influence of scene memory into preview paradigm, and the relationship between attention and feature binding in the context of the unexpectedly efficient triple conjunction search. However, this model was limited to classical laboratory stimuli. The goal was to understand the neural process behind the categorical visual search in natural scenes. But unfortunately, little is known on how humans guide visual search for categorically defined targets in natural scenes. There is some evidence that color and pre-attentive shape are some of the few features that guide visual search for natural objects, but what this pre-attentive shape really is remains an unsolved question. Our solution is to extract these pre-attentive shape guidance features from an intermediate layer of the CNN model and learn the association between them and categorical concepts. Searching for objects implies learning object templates for object recognition, and our solution is to embed a headless deep CNN as a feature extraction network into our DFT model. Anchor objects and their reproducible spatial relation to other objects enable humans to strongly reduce the area scanned in visual search. This is called scene grammar. We also will propose a new neural process account for scene grammar. This is an overview of the neural architecture. At the first glance, it seems quite large and complex, but since it's able to solve many different cognitive processes at the same time, it is strongly constrained. And these neural processes are, for example, extracting feed-forward features and creating saliency maps from visual inputs, the attentional selection through bias competition, and feature binding in the sense of N-Treatment's feature integration theory, match detection between expectation and perception, learning the association between the complex foveal features at attended location and the categorical concept for object recognition, and learning the association between the concept and the retinal pre-attentive features as attentional guidance template. Autonomously visual exploration of the scene and simultaneously building a scene memory of attended objects. This is a running simulation of the architecture, and I'm going to highlight selected critical moments in time. So a salient location is attentionally selected and the object category is detected. And the category of the recognized object is committed to scene memory. Then a new salient location is attentionally selected and committed to memory. And the process is repeated until there are no more salient locations left. This scene memory can be used to guide visual search or as the basis for other cognitive operations like scene reasoning. The next cognitive operation is visual search for categorically defined target objects in natural scenes. The task is to find a pepper. We see that there's a label cue stored in worker memory, but no color cue. The same is true for the feature matching, where the expectation is to see a pepper without any color requirement. On the top right, we see the guidance features associated with the concept of pepper. The color guidance favors yellow retinal locations since the model was trained on a yellow pepper. A salient location is attentively selected and object category is detected. The expected and attended object category matches, so he found a pepper. And the current location is committed to working memory. The next cognitive operation is visual search for targets object defined by a combination of category and color. As I mentioned earlier, the model prior expectation is that the peppers are all yellow, since everything he has saw in his life was a yellow pepper. So here the task is to explicitly find a red pepper to demonstrate that the attentional guidance template can be flexibly modified by top-down processes that are different from experience. Now there's also a color cue for red stored in working memory, and there's also an expectation to see a red pepper in the feature matching. On the top right, we see that the color guidance was overwritten by a stronger input for red. The first attended location is the yellow pepper, because it happens to have the highest bottom-up saliency that gives it a selective advantage over the competing locations. But since the attended color doesn't match the expected one, a new location is attentionally selected. And this time, color and label matches the expectation of a red pepper, and its location is committed to working memory. The last cognitive operation is a new neural process account for scene grammar. Here the task was to find the mirror in the bathroom. We see that at the beginning. We see at the beginning the label cue is set to mirror, and the expectation is to see a mirror or to find a mirror. The information that there's a known anchor, in this case the sink, is transferred from long-time memory to working memory. And the information that the mirror is expected to be above the sink is also transferred from long-time memory to working memory. Please keep in mind that all these processes emerge autonomously from the underlying neurodynamics. We also see that the expectation to see a mirror was replaced with the expectation to see a sink. Here we see how the change in expectation changes the attentional guidance template in working memory, as there is a shift of saliency in the input in the attention field that now highly favors the sink, which is then selected and recognized. Now that the location of the anchor object was found, its position is committed to working memory. And a spatial bias for above is induced at the found location, and the expectation switches back to mirror. A location above the sink is attentionally selected, but no mirror is found there. But also humans will look above the sink, even if there's no saliency that would expect there to be a mirror. So we have shown a neural process account for visual search and scene memory that autonomously builds a scene representation and performs guided categorical visual search in natural scenes. We found solutions for 3 important problems: how the association between a categorical concept and pre-attentive shape can be learned from the intermediate layer of a CNN, and how the distributed representation of the CNN feature maps can be mapped to the localist representation of a dynamic neural field, and how scene grammar emerged from the underlying neurodynamics. To our knowledge, this is the first model to account for it. Thank you for your attention, and I'm happy to answer your questions.